This screencast is about checking the multiple linear regression model assumptions, called residual analysis. The multiple linear regression model assumptions are the same as for simple linear regression: line, linearity, independence, normality, and equal variance. In multiple linear regression, the additional number of independent variables increases the number of scatterplots required to check the linearity, also called fit, and the equal variance, also called homoscedasticity assumptions. Checking the independence and normality assumptions are exactly the same as in simple linear regression. Let's discuss the scatterplots required and what to look for on those scatterplots. It's important to remember that on all our scatterplots, the residual values will appear on the vertical axis. The scatterplots required to check the linearity model assumptions are the fitted values versus the residual values, the values of the first independent variable versus the residual values, the values of the second independent variable versus the residuals, all the way down to the values of the kth independent variable versus the residuals. If all of these scatter plots appear as random scatter without significant curvature, then the linearity assumption is satisfied. The independence assumption needs to be checked only when data is collected in a time sequence. When the data is collected in a time sequence, a time series plot of the residual values is required. If this time series plot appears as random scatter, and if the hypothesis test for positive autocorrelation shows that there is no positive autocorrelation, then the independence assumption is satisfied. The normality assumption is checked with a normal probability plot constructed exactly as in simple linear regression. If the normal probability plot appears as an approximate straight line, then the normality assumption is considered satisfied. Checking the equal variance assumption uses the same scatter plots as we use for linearity. If those scatter plots again appear as random scatter, specifically in this case a lack of cone shape, then we conclude the equal variance assumption is satisfied. We've moved to the next page. On this page we begin a residual analysis to check the model assumptions for the multiple linear regression model that uses both radio advertising expense and newspaper advertising expense to predict sales. The first plot we'll look at is the fitted values on the horizontal axis versus the residual values on the vertical axis. This data appears at the bottom of the regression output. Here is that scatter plot. This is the fitted value axis, and this is the residual value axis. We note that the residual values appear to be large, greater than 0 for smaller fitted values, and less than 0 in the middle of the fitted value range, and once again tend to be higher than 0 on the larger side of the fitted value range. This plot is clearly marginal. It puts the linearity assumption in doubt and makes it hard to get any kind of read on the equal variance assumption. The next plot we'll look at is that of the x1 variable, the first independent variable, radio advertising expense on the horizontal axis, versus the residual values on the vertical axis. These columns must be recopied and pasted on an Excel spreadsheet. Here is the resulting scatter plot. Again, radio advertising values appear horizontally and residual values appear vertically. Again, curvature is evident on this plot. And this curvature places the linearity model assumption in doubt. Now let's take a look at the plot of the second independent variable, newspaper advertising expense, placed on the horizontal axis, and again the residual values placed on the vertical axis. These columns must also be copied and repasted on an Excel spreadsheet. Here's the plot. Values of newspaper advertising expense appear horizontally and residual values appear vertically. Again, a certain amount of curvature appears in this plot, which again puts in question the linearity model assumption. A comment on the curvature we've observed on these two residual scatter plots. That curvature may in fact be reinforced by, for example, in the case of the residual values versus the radio advertising, the two cities where there was zero expenditure on radio advertising expense, and looking back at the data, a rather high expenditure on newspaper advertising expense. In the case of the second scatter plot, there were two cities where newspaper advertising expense was at zero, but looking back at the data, those two cities had a relatively high radio advertising expense. We'll make some summary comments on the model assumptions in a moment, but for now, let's move to the independence model assumption. Since the data was not collected in a time series, we will assume by default that the independence model assumption is satisfied. We've moved to the next page where we'll construct an NPP of the residual values. Here are the data value ranks. There are 22 observations in our data set. Here are the proportions. The first proportion is 1 over n plus 1, in this case 1/23rd, and then 2/23rds, and then 3/23rds, all the way down to 22/23rds. This is the column of the z-values. The first z-value is obtained using the function equals normal s. It's actually norm s inverse of the proportion immediately to the left. And this is equal norm s inverse of the proportion immediately to the left of that entry, and so forth. And that function was pulled down through this column. And next to the z-value column are the ranked residuals from the largest negative residual to the largest positive residual. When we construct the scatter plot of the z-values versus the ranked residual values, we get a normal probability plot of the residual values, and this one clearly appears to be very close to a straight line. Our conclusion is the normal model assumption is satisfied. Our overall evaluation of this model is that the model assumptions are at best marginal. We could use the model if we can't find a better alternative, but we would have to be very careful on how we interpret any kind of statistical results that we would derive from this model. This will end this screencast.